Hi guys, welcome back. Today we're going to continue our conversation on the citric acid cycle. So to begin, I've just included a general diagram of this cycle. It consists of 8 steps, and I say that lightly because this is a truly cyclical process with no real start or end point. However, the cycle cannot proceed without the input of acetyl-CoA produced from the conversion of pyruvate. And just remember, pyruvate is the main product of the glycolysis pathway, and this is just one of those alternate pathways or destinations for pyruvate post-glycolysis. And this citric acid cycle involves the use of a lot of intermediates such as citrate, succinyl-CoA, and oxaloacetate. However, what we really focus on are the products, what is produced from the citric acid cycle. So from one round, we have 1 molecule of ATP, 3 NADH, and 1 FADH2 molecule being generated. However, glycolysis actually produces 2 molecules of pyruvate. So in reality, 2 acetyl-CoA molecules are entering the citric acid cycle. So as a result, you have to double the products. So there's now 2 ATP molecules, 6 NADH, and then 2 FADH2 molecules. And today, what we're really focusing on are the NADH molecules. And there are 3 separate steps in this cycle where NADH is produced. The first being the step where isocitrate is converted to alpha ketoglutarate. The next is where that alpha ketoglutarate is converted into succinyl-CoA. And then finally, where malate, specifically L-malate, is converted to oxaloacetate. And we'll look further and more in depth at each of these steps next. So this is the 3rd step of the citric acid cycle. Again, isocitrate converted to alpha ketoglutarate. And this reaction involves the use of the isocitrate dehydrogenase enzyme. This is important. Make sure you know that, just because when you're asked to draw this pathway out, if you don't have that enzyme, you will lose points. It's a unidirectional reaction, meaning isocitrate can be converted to alpha ketoglutarate with this enzyme, but not the reverse reaction. And then something else I really want to note is the leaving of CO2 as a product. You have to make sure you draw this CO2 leaving on any diagram. So next is this next step, step 4, where alpha ketoglutarate is converted into succinyl-CoA. This is a unique reaction because you actually see the input of that CoA back into the reaction. We also, again, see the reduction of NAD+ to NADH, and this step uses the enzyme alpha ketoglutarate dehydrogenase complex. Finally, we have the last step, again in quotation, step of the citric acid cycle, where malate is converted to oxaloacetate, specifically L-malate. It's the active form of malate. If it's in any other form, it's basically useless and the citric acid cycle cannot proceed. So as a result, the enzyme used is L-malate dehydrogenase. And again, we see the reduction of NAD+ to NADH, and that is it. So why is it so important? Why are we really focusing on the steps where these NADH are produced? And it is because NADH, as well as FADH2, are used in the process of oxidative phosphorylation. And it is in this pathway where we see a majority of the ATP needed by our bodies is produced. So something to just keep in mind is that for every 1 molecule of NADH, 2.5, so 2.5 ATP molecules are produced during oxidative phosphorylation. So we have 6 molecules of NADH being produced from 2 rounds of the citric acid cycle. So 6 times 2.5 is 15 molecules of ATP. And while this may not seem that much in the grand scheme of things, when the citric acid cycle is constantly pushing and pumping out 6 NADH molecules, the concentration of ATP builds up, and that ATP can then be used by our bodies in a multitude of different processes to complete whatever it needs. So that is why the production of NADH is so important, and in turn, why the citric acid cycle is incredibly important. So that pretty much wraps up our discussion for today. Thank you guys for listening, and I'll see you next time.